Hello, Coach Travis here with another trigonometry video. So what we want to do in this video is I want to show you how you can build the inverse secant function. So building the inverse secant function and inverse cosecant function, the ideas are the same as when we built the inverse sine, the inverse cosine, and the inverse tangent function. So I hope you kind of see the pattern at this point. But because secant and cosecant are kind of complicated functions, building their inverses, again, it's the same pattern, it's the same idea that we've seen before, but the details are a little bit more complicated because the secant function and the cosecant function are a little bit more complicated. So what we got here on the on Geogebra is we've got the graph of the secant function. So this is the good old secant function here. And so obviously this function does not have an inverse. So when you see this function, you should say this function does not have an inverse because it fails the horizontal line test. So this horizontal line touches in multiple places, and anytime that happens, then that means your function does not have an inverse function. So the regular secant function does not have an inverse. So we've seen this before. What do we do then? So what we do is, in some sense, we cheat. Is that we don't take the entire secant function. We just take what we call the restricted secant function. So all right, so there shown in black, that is the restricted secant function. So I only take the part of the secant function that I'm showing here in black. So let's go ahead and get rid of the old one. And it's actually maybe worth pointing out here, in order to draw, you might wonder, hey Travis, how did you do that? How did you get Geogebra to draw this? So you have to do a little bit of fancy Geogebra language to do this. But essentially what you do is you use this function that's called the curve function. So I tell Geogebra to graph a curve, and then I tell it what the x-coordinate is going to be, and then I tell it what the y-coordinate is going to be, and then I tell it the values that the t is going to take. So t is going to range from 0 to pi. And so this is actually called a parametric curve, and you'll learn more about parametric curves. You'll do a little bit in second and third semester calculus. So if you take more advanced calculus, you'll learn more about graphing things using parameterizations, and that can allow you to do some real cool stuff. So anyway, so that's a sales pitch for taking second and third semester calculus. So anyway, so what we got here is we got the restricted secant function, and so this does pass the horizontal line test. So this function does have an inverse. But before we draw the inverse, let's just make a note of like what the domain and range are, because that's going to be, because again, this is kind of a weird function. So let's just make sure part of understanding a function is not just understanding what the graph looks like, but understanding what the domain and the range are. And so if you look at this, like the domain, we said, well, looks like we started with x being equal to 0, and we said we end with x being around 3. But you should know from experience that when you're dealing with trig functions, whenever you have something that's around 3, that's probably pi. So this is actually, so let me write that down, that the upper bound here for x is actually at pi. So, all right. So we got that. Oh, but wait, there's an asymptote in here. And it looks like that vertical asymptote occurs at about 1.5. And again, you should know at this point in your life, you should know from experience that when you're dealing with trigonometry, and you have a number that's around 1.5, then that number is actually probably pi over 2. I did not draw a very good pi there, so let's... Okay, so that's the vertical asymptote is at pi over 2. Okay, so that gives us our domain then. So the domain of the restricted secant function is we go all the way from 0 to pi over 2, but then we have to skip pi over 2, and then we start again and we go from pi over 2 to pi, but we have to skip the pi over 2. So that's why we have the round brackets there, but we have the square brackets on the ends. Okay, great. So that's the restricted secant function right there. And now we think about, okay, how do we get the inverse? Okay, well, we know to get the inverse, what we have to do is we have to reflect the graph across the line y is equal to x. So here we got this dotted line, and this dotted line or dashed line is that's the graph of y is equal to x. So if I just imagine reflecting these two pieces across that line, it's kind of a tricky thing to do, but if you had graph paper, you could draw it out. And what you get is you get this picture, this guy here in blue. And if you stare at that long enough, you'll say, yeah, okay, is the black curve, is that the black curve and the blue curve, are those reflections across this red line? And I think they are. And actually what's really cool, what I like about this algebraically, is if you look at what I typed into Geogebra in order to get Geogebra to draw this inverse secant function, notice what I did here. I typed exactly the same thing I did, right? So right here is in black is the restricted secant function. And then here in blue is the inverse secant function. And notice I typed in exactly the same thing. The only difference is I switched the x's and the y's. So like for the secant function, y was the secant of t, but for the inverse secant function, the x was the secant of t. And that's because, again, when you think about inverses, what you should think is inverse functions they're two sides of the same coin. They're the same function, only the x's and the y's get switched. So whenever you have a function, if you just take all the points on that function and you literally switch the x's and the y's, then you get the graph of the inverse. All right, so anyway, so there we go. So let's clean this up here. And there we go. So now there's your graph. There's your inverse secant function. So if you want to know what the graph of the inverse secant function looks like, or you want to know what does the inverse secant function look like? What's its domain? What's its range? Here it is. And so again, algebraically, we should be able to predict the domain and range, because we know that when you go from a function to its inverse, the domain and the range should just trade places. So the domain here should be the range here. And the range of the original function should be the domain of the inverse function. So we predict that algebraically. But let's just look at the picture and verify that this is right. So if I look at this picture, I see that, what do I see? I see that the domain, well, it looks like we start with x being equal to 1, and then we all go all the way up to probably x is equal to infinity. Okay, so that gives us this part. And then over here, we start with x is equal to -1, and then we go all the way out to -infinity, and so that's what gave us this part. So sure enough, the domain, this is the domain of the inverse secant function. And now let's look at the range. Okay, well, let's see. The lowest we ever go is at 0. And then we go up, but it looks like we have a horizontal asymptote that we never cross around 1.5. Oh, yeah, but remember that when you're dealing with trig functions, whenever you wind up with a 1.5, that's probably pi over 2. So what we got here is we've got that the range is going to go from 0 up to pi over 2, and it never reaches pi over 2. So that's where we got that piece right there. And then we start at pi over 2, and then we go up until we're a little bit bigger than 3. But once again, when you're dealing with trigonometry, whenever you're a little bit bigger than 3, that's probably pi. And in this case, it is. So the range is everything from 0 to pi, except you have to skip pi over 2 because there's a horizontal asymptote there. And so sure enough, we predicted that algebraically, but it's nice when the graph agrees with what you expect algebraically. So anyway, so there you go. So there's the inverse secant function. And so again, the emphasis here is this was the same process that we've done before. That is, let's go through it real quick again, just to review. So you start with your trig function, but your trig function doesn't have an inverse because it fails the horizontal line test. So then what you do is you restrict your trig function. So you restrict your trig function so it does pass the horizontal line test. And then once you got that, once you pass the horizontal line test, then you know you have an inverse, and that's where you get your inverse from. So we've done this before, but again, it is kind of complicated with the secant function because the secant has a weird domain and range, and as a result, the inverse secant is going to have a weird domain and range. But mathematically, the ideas are all the same.